Hello Precalc. We are in the middle of the 2-2 day 1 note sheet. So in the last video we finished number 5. I kind of got cut off just a little bit because my videos are set to only 15 minutes max. So we showed that it equaled 5. Technically, with notation, you'd say the limit as x approaches infinity of 5x plus sine of x all over x is equal to 5. So you do kind of need that at the end, but no matter. So what we're going to do is we're going to move on to the next part, which is limits, infinite limits as x approaches a. Okay. So what we've got is we're going to sketch f of x equals 1 over x and determine the following. We're going to find the limit as x approaches 0 from the right and the limit as x approaches 0 from the left. So 1 over x, common graph, we did this at the beginning of this note sheet. We know that we have a branch that looks like this, a branch that looks like this, and we know that there's a vertical asymptote here and a horizontal asymptote going along y equals 0. From there, limit as x approaches 0 from the right. Okay, so as we approach 0, all right, and we're going to the right, what's going to happen? So here's 0. This is my vertical asymptote. As we approach that vertical asymptote from the right, so if you follow the right branch, as we get closer and closer to that vertical asymptote, we're going up and up and up and up, which means that we are approaching positive infinity. As we approach 0 from the left, so as we approach this vertical asymptote from the left, notice we are getting closer and closer to that vertical asymptote, and it keeps going down, 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 which means that we're going to be approaching negative infinity. Okay, so the limit as x approaches 0 from the right is positive. The limit as x approaches 0 from the left is negative. Technically, if you were asked to find the limit as x approaches just 0, it would be does not exist because these are not the same. All right, the vertical asymptote, by the way, for this problem, we know is x equals 0. So basically, we were doing a problem that involved a limit approaching the vertical asymptote. With a vertical asymptote, if we have the line x equals a is a vertical asymptote, if either the limit as x approaches a from the right of f of x equals plus or minus infinity, or the limit as x approaches a from the left of f of x equals plus or minus infinity. So you can tell that this value a is a vertical asymptote if you find the limit whether you're going from the left or the right and it equals infinity or negative infinity. All right, which hopefully that makes sense. As you approach a vertical asymptote, you're not actually going to get to cross it. It's either going to make you keep going up or make you keep going down, and so it's positive or negative infinity. What we're going to do with these is we're going to be doing some limits involving x approaching a vertical asymptote. Like in number 6, you can tell the vertical asymptote is going to be 3 because 3 makes the denominator 0. So we're approaching this vertical asymptote from the right and the vertical asymptote from the left. Normally, we would plug it in and see what it equals. We can't do that because it makes it undefined. We also can't really factor this to like cancel things out like we've done in the past. So it's kind of tricky, all right? We can't plug in 3, we can't factor it or anything like that. So what we're going to do is, because we know this is a vertical asymptote, we know that as we approach from the right, we're either going to be going up or down to positive or negative infinity. We also know that as we approach it from the left, we're either going to be going up or down, depending on what the graph looks like. And we're trying to do this without looking at the graph. So we know our answer is going to be either positive infinity or negative infinity, depending on what we have. What we're going to do is we can't plug in 3. Since we're coming from the right, that means we're coming from numbers that are bigger than 3. What we're going to do is we're going to let x be a little bit bigger than 3. So we're going to let x equal 3.01. You can pick whatever you want. I'm just making it a little bit bigger than 3. When you pick a value just a little bit bigger than 3 and you plug it in, it doesn't even matter what the specific number value is. Just plug it in. If you do 3.01 squared times 2 minus 3, you're going to get some kind of a positive value. If you plug in 3.01 minus 3, you're also going to get a positive value. Since positive divided by a positive is positive, that means it's going to be approaching positive infinity. And then you do the same thing down here. All right, the limit as x approaches 3 from the left. Since we're coming from the left, that means we're coming from numbers that are a little bit smaller than 3, so we're going to let x equal 2.99. When you let x equal 2.99 and you square it, times it by 2, minus by 3, you're going to get a positive value. You can always use your calculator if you're not sure. 2.99 minus 3, you're going to get a negative value. Positive divided by a negative is a negative, so that means we're going to be approaching negative infinity. All right, so that's kind of the trick you can do with vertical asymptotes because we know it's automatically infinity. It's just a matter of positive or negative. Same thing for this guy. -2 you can tell is a vertical asymptote because -2 makes the denominator 0 and we can't cancel anything out, we can't factor. So when we do this first one, since it's coming from the right, we're going to let x equal something a little bit bigger, so 2.01. And when you plug it in, you're going to have obviously a positive number, not infinity. You're going to have a positive number on top, the 1, and then 2.01 plus 2 squared is also positive. So this is going to be positive infinity. This one, if you do from the left, x is going to be a little bit smaller than 2, so 1.99. You're going to get a positive over another positive. So this is positive infinity. All right. Something to be aware of is if you notice, this first one that we did was x minus 3. You could think of it as x minus 3 to the first. Notice that when you have an odd degree, you're going to have the different limits are going to be opposites. All right, they're going to be different directions. Okay, different directions. One's positive infinity and one's negative infinity. With this one, you'll notice we had a even power. Okay, if you have an even power, so if this was to the 4th power, 6th power, whatever, then they're always going to go the same direction. Okay, so if you have, if this was x minus 3 to the 3rd, x minus 3 to the 5th, one would be positive and one would be negative infinity. If these were both even numbers, they're both going to be positive or both are going to be negative. They'll be the same. This last one is a real doozy. This last one, when you plug in 2 into the denominator, you do get 0. So it makes you think that there is a vertical asymptote at 2. The trick with this one, though, is if you plug in 2 into the numerator, okay? If you plug in x equals 2, you're going to get 0 over 0. Okay, if you plug in 2 into the numerator, you're going to get 0. If you plug 2 into the denominator, you're going to get 0. That means that there isn't a vertical asymptote at x equals 2. This means that there's a hole at 2. Okay, there's a hole at x equals 2. If there's a hole at x equals 2, that means that, okay, therefore, x minus 2 has to be a factor of the denominator. All right, and the top as well. X minus 2 is a factor of the top and the bottom. The bottom is yucky to factor, but we're going to do it. The numerator also factors much more easily than the bottom. All right, if you factor the top, you're going to have x minus 2 times x plus 3. The bottom, no idea. But we do know that x minus 2 is a factor, so what we're going to do is we're going to go way back to something that we did a while ago, and since we know it's a factor, we're going to do synthetic division. All right, so 2 is a factor. And remember, you take the numerator, or not the numerator, I apologize, the coefficient of each term. All right, make sure each term is represented. X cubed, x squared, x, no x. So we got 3, 5, negative 23, and 2. Remember, you bring down the first term. 2 times 3 is 6. Add those together, you get 11. 2 times 11 is 22. Add those together, you get -1. 2 times -1 is -2. You should get a 0. This is your remainder, this is your constant, this is your x, this is your x squared. So the denominator, we already know that 2 is a factor, so x minus 2 is going to go there. And then the rest of it is 3x squared plus 11x minus 1. And then from there, we can cancel those out. And now we can find the limit as x approaches 2. So the limit as x approaches 2 of this x plus 3 all over 3x squared plus 11x minus 1. You can just plug the 2 value in. It will no longer make it undefined. You're going to get 5 over 33. So that one's kind of a tricky one because you have to do synthetic division to help you factor the bottom out a little bit. All right, so there's number 8. Let's go to the last page. End behavior. Okay, end behavior model is pretty easy. What you're going to do is you're figuring out whether the end behavior, so what the ends of the graph are doing, if they're approaching positive infinity or negative infinity. When you do end behavior model, you don't have to worry about factoring this whole crazy thing out. What you're going to do is you're going to just focus on the highest degree term for both the numerator and denominator. So essentially what we're looking for is the limit as x approaches infinity of 2x to the fourth over x squared, because the rest of this isn't going to change the graph very much. Now when you simplify this, this is the same thing as the limit as x approaches infinity of just 2x squared. All right, now 2x squared, you can think about that kind of a graph, or you can plug in infinity if you want to. But think about it, x squared, 2x squared is going to be a parabola that opens up. As you approach infinity, you're going up, 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 which is positive infinity. If you do for negative infinity, okay, the limit as x approaches negative infinity of this whole crazy thing. Actually, I'm not even going to rewrite. I'm just going to put it right here. The limit as x approaches negative infinity. As you go to the left, it's going up, 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 up. So that's going to be positive infinity. All right, so both of these limits approach positive infinity. All right. And you just do the end behavior model. Very simple. All right, for number 10, same idea. I'm going to combine like terms a little bit. The 2, I need an x plus 1. So I'm going to multiply by x plus 1, x plus 1. So I get 2 times x plus 1 minus x all over 2 times x plus 1. Oh, I forgot to multiply the other guy by 2. Sorry. Oh, no, I don't need to do that. So, there we go. Don't need the 2 in the bottom. When we combine like terms, we're going to get 2x plus 2 minus x all over x plus 1. We're going to get x plus 2 all over x plus 1. And then this guy, so we've got x plus 2 all over x plus 1. And we're multiplying it by x squared all over 3 plus x squared. All right, we're going to have to multiply that all out together. You're going to end up with x cubed plus 2x squared. And then the denominator, if you multiply these together, you're going to end up with x times 3, 3x. X times x squared is x cubed. 1 times 3 is 3. 1 times x squared is x squared. And you're going to end up with x cubed plus 2x squared all over x cubed plus x squared plus 3x plus 3. All right, and we're doing the limit as x approaches infinity. For the end behavior model, you're just going to take the highest term for both the numerator and the denominator. So essentially, we're doing the limit as x approaches infinity of x cubed over x cubed. Well, x cubed over x cubed, that's 1. So the limit as x approaches infinity of 1, that's just going to be 1. So our answer is just 1. Okay, technically, that means that there is a horizontal asymptote at y equals 1. Okay. For the last one, okay, we're going to do the limit as x approaches infinity of 1 over x minus 1. Again, you can just take the highest degree term. So we're doing really the limit as x approaches infinity of 1 over x. We've already done that. All right, the limit as x approaches infinity of 1 over x, we know it's approaching that horizontal asymptote of 0. So the limit is going to be 0. Okay, this one has a horizontal asymptote of y equals 1, and this one has a horizontal asymptote of y equals 0. All right, so that's end behavior model. That's the only time you're going to do this is when it actually says use end behavior model. All right, otherwise you can't do that for just normal limits. All right, thanks for listening.